soutenance de thèse de doctorat en télécommunication intitulé Design of New Antenna for Biomedical Applications, présenté par Getar Bileb, devant le jury composé par professeur Badra, Université de Khanchla, professeur Ouadek Hassan, Université de Guema, donc encadré par professeur docteur Chahben Abdelhadi et docteur Khaled Abdelzak, présidé par moi-même, professeur Baroya Abdelsalam. Donc, monsieur Guetta, vous avez 30 minutes pour exposer l'essentiel de votre travail de thèse. Bon courage.
Bismillahirrahmanirrahim. Assalamu alaikum. Mr. President, esteemed jury members, my supervisors, and dear guests, today I have the honor of presenting my PhD dissertation upon you. This presentation focuses in our PhD dissertation research work entitled Design of a New Antenna for Biomedical Applications, under the supervision of Dr. Chahben Abdelhadi and Dr. Khaled Abdelzak. The presentation is divided into 4 parts. It begins with introduction, followed by recently reported antennas. After that, it introduces our results and discussions. Finally, the presentation ends with the conclusion and perspective. Let's start with introduction. Antennas play a crucial role in medical sector. We take up with your application categorized into 3 distinct domains: diagnostic applications, illustrated by techniques such as magnetic resonance imaging and medical microwave imaging. The transmission of data, commonly known as biomedical telemetry, which can be classified as wearable antennas, implantable antennas, or adjustable antennas. Therapeutic applications, specifically in radio frequency thermal ablation, with notable application in cardiology and cancer therapy, particularly tumor ablation. Firstly, let's delve into the role of antennas in medical microwave imaging. Medical imaging exploits physical phenomena such as X-ray, radioactivity, magnetic resonance, ultrasound, and MRI. Medical imaging exploits physical phenomena such as X-ray, radioactivity, magnetic resonance, and MRI. Medical imaging exploits physical phenomena such as X-ray, radioactivity, magnetic resonance, and MRI to generate visual representation or images of body tissues, anatomy, and organs. The most commonly used imaging modalities in clinical medicine include radiography, mammography, computerography, ultrasound, and MRI, but these screen approaches are quite costly, painful, ionized, and offer poor image resolution of these scanned body tissues. Another method for medical imaging, which is in the interest of many researchers, is the microwave imaging. It's a proficient method for early-stage cancer detection and stroke detection because of its non-ionizing radiation, cost-effectiveness, safety, simplicity, and offer high image resolution of these scanned body tissues. Medical microwave imaging techniques provides better sensitivity and the ability to detect small tumors and small brain strokes because of it's based on the dielectric properties contrast between abnormal tissues and normal tissues. Microwave imaging is a technique used to detect hidden or embedded objects inside a medium user microwave, and the fundamental premise of microwave detection is the sharp contrast in the dielectric properties of abnormal tissues in comparison to healthy tissues. Therefore, knowledge of the dielectric properties of body tissues is essential for the understanding of the interactions between the electromagnetic fields and the body tissues. In quantitative microwave imaging, the dielectric properties are constructed regarding the differences in the complex permittivity, while non-metallic materials are considered biomedical applications, defined by the following equation, where the real part represents the ability of the material to store microwave energy, whereas the imaginary part, or the loss factor, indicates the ability of the material to absorb microwave energy. A microwave imaging system is based on 2 main parts, part hardware and part software. Part hardware or antenna is responsible for eliminating and collecting microwave signals under tests such as head and breast. Part software or post-processing algorithms that are responsible for reconstructing image of the target object. Microwave imaging is categorized into 3 types: monostatic microwave imaging, bistatic microwave imaging, and multistatic microwave imaging. Monostatic microwave imaging involves the use of a single antenna serving both as a transmitter and a receiver. In bistatic microwave imaging, 2 antennas are employed, with one acting as a transmitter and the other as a receiver. Multistatic microwave imaging utilizes an array of antennas, with one antenna operating as a transmitter at a given time, while the others function as receivers. Now let's explore the role of antennas in biomedical telemetry. Biomedical telemetry involves the process of measuring signals originating from the body and transmitting them to a remote base station, such as phone or PC, over an RF communication link. Subsequently, this data sent over the internet to a doctor or relevant individual for diagnosis and guidance to the patient. The accompanying figure illustrates a remote base station healthcare monitoring system with either invasive and non-invasive sensor nodes deployed on the human body. The physiological parameters are transmitted to the monitoring unit for further analysis using the integrated antenna. Antennas designed for biomedical application can be classified as wearable antennas, implantable antennas, or ingestible antennas, depending on the location of the sensor nodes on or inside the human body. Wearable antennas are strategically positioned on various body parts for continuous monitoring of vital parameters. They enable non-invasive sensor nodes, monitoring vital parameters such as skin temperature, blood pressure, and glucose level. Challenges in wearable antenna design include body influence, but techniques like circular polarization and impedance matching can address them effectively. The shape of antenna in medical circuits is influenced by the body's organs and the location of use. Implantable medical devices are permanently or semi-permanently embedded semi-permanently or semi-permanently embedded to address health conditions. These devices are typically placed between 2 to 3 centimeters beneath the skin and connected to organs like the brain and the heart. Ingestible antennas in capsule endoscopy transmit biological data through a camera embedded in capsule as it moves through the digestive system, aiding in detecting conditions like Crohn's disease and tumors. Wireless capsule endoscopy offers comfort and effective visualization with components including an antenna for real-time data transmission. Radio spectrum allocation for wireless medical application varies by the region and it is regulated by accredited bodies with categorization based on licensing approaches and spectrum sharing. Antenna engineers select operating frequency band and antenna engineers select operating frequency bands based on these specific applications. Lower frequencies minimize signal losses in biological tissues, while higher frequencies enable faster communication with smaller antenna dimensions. Several antennas have been reported for biomedical applications, as presented in this table. However, these antennas are linearly polarized and serve only one use, whether for cancer screening, stroke screening, or health monitoring. Thus, novel high-performance antennas are needed for several biomedical applications. To address this need, in our dissertation, we proposed a narrow-band circularly polarized antenna for medical microwave imaging and health monitoring applications. Figure 2 shows the evolution of the proposed antenna during the design process. A prototype of design antenna was fabricated and printed on a low-cost FR4 substrate with a compact size of 34 by 28 millimeters and a thickness of 1.3 millimeters. The proposed antenna is optimized to operate in the industrial, scientific, and medical band, as shown by reflection coefficient in blue in figure 3a. With the simulated impedance bandwidth between 2.425 and 2.475 gigahertz. It decreases to less than minus 30 decibel at a resonance frequency of 2.45 gigahertz. The proposed antenna also exhibits a circular polarization performance at 2.45 gigahertz with a simulated axial ratio of 0.98 decibel and an axial ratio bandwidth of less than 3 decibel between 2.438 and 2.463 gigahertz. The generation of circular polarization is attributed to the presence of two slots and a stub inserted on the ground plane, as shown in figure 1b. The circular polarization is evident from the surface current direction as changes in phases. As shown in figure 4, we examined the distribution of the current on the antenna's surface at 2.45 gigahertz for four different phases: 0, 90, 120, and 80, and 270 degrees. This result indicates that the main current direction is in the minus at 0 degrees at the minus x direction. At 90 degrees, it shifts to the plus y direction. For 180 and 270 degrees, the directions are reversed compared to 0 and 90 degrees. Consequently, the main surface current rotates clockwise, signifying that a left-hand circular polarization is acquired in the direction of propagation with the proposed antenna. Figure 5 presents the setup for measuring reflection coefficient of the proposed fabricated antenna using the vector network analyzer. The measured impedance bandwidth between 2.32 and 2.51 gigahertz. As illustrated in figure 7, the simulated and measured reflection coefficient of the proposed antenna are in good agreement. The suitability of the proposed antenna for medical microwave imaging is confirmed by its ability to detect the presence, size, and position of breast tumors and brain strokes. First, the hemispherical breast phantom model was simulated. It's composed of 3 layers: skin, fat, and fibroglandular. The properties of the human breast phantom model and the tumor model at 2.45 GHz are given in table 2. Then, the proposed antenna was placed at a safe distance of 10 millimeters from the healthy breast phantom model as depicted in figure 8. A spherical tumor with a radius of 2.5 millimeters were inserted at 4 different positions inside the human breast phantom model as depicted in figure B. The reflection coefficient of the proposed antenna and the human breast phantom model having a tumor at 4 different positions of distances 15, 30, 40, and 50 millimeters from the antenna and without tumor is presented in figure 10. It's clear that the shift in the resonance frequency is inversely proportional between the distance between the antenna and the tumor. Then, tumors of 3 different sizes with the radii of 4, 7, and 9 millimeters were inserted at a fixed position inside the human breast phantom model as depicted in figure B. The reflection coefficient of the proposed antenna and the human breast phantom model with and without tumor is presented in figure 12. It reveals that the shift in the resonance frequency and the adaptation level is more noticeable for larger tumor sizes. Thus, as the tumor sizes increases, its detection becomes easier. The capability of detecting brain strokes using the proposed antenna was validated using a spherical human head phantom model as depicted in figure 13. It's composed of 7 layers: skin, fat, muscles, skull, cerebrospinal, and brain. The properties of the human head phantom model and the stroke model at 2.45 GHz are given in table 3. First, the proposed antenna was positioned at a safe distance of 5 mm from the healthy head phantom model as depicted in figure A. Then a spherical blood clot with 2 different radii, 5 and 13 mm, were inserted at a fixed position on the human head phantom model as depicted in figure B. The reflection coefficient of the proposed antenna and the human head phantom model with and without the stroke is presented in figure 15. A shift in the resonance frequency in the cases of brain strokes is clear. Figures 16, 17, and 18 shows the current density, magnetic field, and electric field of the proposed antenna at 2.45 GHz. These results indicate that the current density, magnetic field, and electric field values decreases in the presence of the brain strokes, which predicts its existence on the human head. Slight adjustments were made to the dimensions of the slot in the linearly polarized antenna 2, shown in figure 2 of the evolution of the proposed antenna during the design process, to shift the resonance frequency to 2.45 GHz. The proposed linearly polarized antenna was positioned at a safe distance of 5 mm for demonstrate the advantages of circular polarization in detecting brain strokes. The reflection coefficient of the linearly polarized antenna and the human head phantom model with and without stroke is presented in figure A. It reveals that there is no shift in the resonance frequency compared to the results obtained with the circularly polarized antenna. Table 5 indicates that the circularly polarized antenna is more effective than linearly polarized antenna in detecting brain stroke, because the circularly polarized waves penetrate body more deeply. The proposed circularly polarized antenna was then simulated in a human arm phantom model and on a real human arm to check its usefulness for health monitoring applications. First, first portion of human arm phantom model was designed. It's composed of 4 layers: skin, fat, muscle, and bone. The properties of the considered arm phantom model at 2.45 GHz are given in table 7. Then, the proposed antenna was positioned at a safe distance from the human arm phantom model as depicted in figure A. Figure B indicates that the resonance frequency of the proposed antenna has a slight shift in the resonance frequency compared to antenna without human arm phantom model. Due to the high dielectric properties of body tissues, nonetheless, the proposed antenna, in the presence of the human arm phantom model, has a simulated impedance bandwidth between 2.438 and 2.489 GHz, and a reflection coefficient level of minus 13.28 decibel, which covers the desired ESM band. The usefulness of the proposed antenna for wearable health monitoring applications was then checked experimentally by placing the fabricated prototype on a real human arm, as depicted in figure 24. The simulated and measured reflection coefficient of the proposed antenna on human arm are compared in figure 25. The volume of the human arm and the gap between the antenna and the human arm are the causes of the mismatch between the simulated and measured values. We conclude from the results that the proposed antenna is suitable for wearable health monitoring applications. Specific absorption rate parameters of the proposed antenna was analyzed on breast, head, and arm of the human phantom models. Specific absorption rate describes how much power is absorbed per kilogram of body tissues. Typically, SAR is averaged across the small volume, either 1 gram or 10 grams of body tissues. In this analysis, the SAR referred to power averaged over 10 grams of body tissues at 2.45 gigahertz. To satisfy the most restrictive SAR regulation, which requires that the SAR is less than 2 watts per kilogram, the input powers must be limited according to the values presented in Table 8. We end our presentation with the conclusion and perspective. In our work, we proposed a monostatic narrowband circularly polarized antenna for medical microimaging and health monitoring applications. A prototype of design antenna has been fabricated and printed on a low-cost FR4 substrate with a compact size of 24 by 28 millimeters and a thickness of 1.5 millimeters. The measured results indicates that the fabricated prototype operates in a narrowband of 195 MHz between 2.32 and 2.51 GHz. Also, the designed antenna exhibits circular polarization in the range of 2.438 and 2.463 GHz. The capability of detection of breast tumors and brain strokes for the proposed antenna was validated using different quantum models. Furthermore, the practicality of the proposed antenna for wearable health monitoring applications was confirmed experimentally. The overall obtained results confirm the effectiveness and usefulness of the proposed antenna for several biomedical applications. The progress achieved in this dissertation should be seen as an advancement in implementing novel medical devices. However, numerous opportunities for future research exist in the domains of both medical microimaging and health monitoring applications. Encouraging perspectives can be envisioned for further exploration. The integration of antennas with other advanced technologies such as artificial intelligence and machine learning could lead to more intelligent and responsive medical devices. This could improve real-time data analysis, diagnostics, and personalized healthcare. Integration with other imaging modalities such as MRI and PET scan may provide a more comprehensive understanding of physiological process. Combining multiple modalities can enhance diagnostic capabilities. Development of flexible and stretchable antenna design could enhance comfort and versatility in wearable health monitoring devices. Such antennas could conform to the body's shape and movement, enabling continuous monitoring without discomfort. The integration of antenna with 5G technology is expected to provide faster and more reliable communication in health monitoring applications. This could support high bandwidth data transmission, enabling seamless connectivity between medical devices and healthcare systems. Thanks for your attention.